Hi everybody, Augie Kennedy here, back with super awesome calculus. And today we're still in chapter 4, which is entitled, what did I call this chapter again? Oh yeah, everything is derivative. And what we're going to do today is we're going to go over a concept that's sometimes taught in Calculus 1 and sometimes put off until Calculus 2, and that is the concept of L'Hopital's rule. Now, before we get to that, last time we looked at how a derivative affects the shape of a graph. We talked about concavity, increasing, decreasing functions, and the first and second derivative tests. What I'd like to do is go over the problem that I gave you, and we'll try to work it out. Alright, so the problem was, I asked you to sketch the graph of a function that satisfies all of the given conditions. And that is that the derivative of the function at 0, the derivative of the function at 2, and the derivative of the function at 4 all equal 0. Also, that the derivative of x is greater than 0 if x is less than 0 or x is between 2 and 4. The derivative of the function is less than 0 if x is between 0 and 2 or x is greater than 4. And the second derivative of x is greater than 0 if x is between 1 and 3, or the second derivative of x is less than 0 if x is less than 1 or x is greater than 3. So, this is a lot of information here, but all of it's pretty maneuverable. So, what we're going to do first is we're going to look at what the f prime 0 equals f prime, let me zoom out a bit. There we go. F prime 0 equals f prime 2 equals f prime 4 equals 0. Right? We know that. What does that mean? Well, that means if the derivative equals 0, we have a horizontal tangent line. So we know that we're going to have a maximum or a minimum at those points. So let's go ahead and let's draw a little coordinate plane here. X, Y, 1, 2, 3, 4, 5, -1, -2, -3. Okay, what we know is that at 0, at some point at 0, at some point at 2, and at some point at 4, horizontal tangent. Alright, now what does this mean? If f prime x is greater than 0, if x is less than 0, or x is between 2 and 4. 2x, 4. Well, what that means is that if the derivative is greater than 0, we know that that is an increasing function. So the function is going to be increasing on this side of 0, so it's going to be increasing. We know we have a flat tangent here. We know we have a flat tangent at 0, a flat tangent at 2, a flat tangent at 4. We know that the function is increasing also between 2 and 4. So in between here, function is increasing. We know that the derivative is less than 0 if x is between 0 and 2. 0, x, 2, or x greater than 4. So what does that mean? Well, if the derivative is less than 0, we know that the function is decreasing, or going down. So that means that between 0 and 2, right here, it is decreasing, and over on this side, it's decreasing. Now, finally, we look at the second derivative. And if we remember some factoids about the second derivative from the last lecture, you may recall that if the second derivative is positive, it's called concave up. It looks kind of like a U. If it's concave down, or if the second derivative is negative, the function is concave down. So, for this function, we know that the second derivative, f double prime x, is greater than 0 if x is between 1 and 3. x, 3. We also know that f double prime x is less than 0, concave down, if x is less than 1 or x is greater than 3. So we know that between 1 and 3, concave up, concave down, and before that concave down. So this is what we know about the function. We've got it all written out here. Concave down between 0 until 2, then it's concave up until 3, and then it's concave down. Increasing until it's 0, then it's decreasing until, when is it decreasing until 2-ish? Yeah. And then it's decreasing again at 4. And we have horizontal tangent lines at 0, 2, and 4. So this graph can look like it can look like many different things. But the way that I would write a graph that matches these conditions would be like so. I would make a graph that is increasing until it gets to 0 at a horizontal tangent line. Alright, so at 0, it's increasing and it's concave down. Sun just came out. Increasing and concave down. Then, at 1, we know the second derivative is going to change from concave down to concave up, so an inflection point there. Notice we have a horizontal tangent line at 0, we need one at 2. So let's put a horizontal tangent right there. And it's going to be concave up until 3 when we have another inflection point. And at that point it's going to go back to being concave down. At 4, it hits a horizontal asymptote, and then it decreases after 4. So that's an example of what a function that matches the aforementioned conditions might look like. Remember, it can look like a couple different things, but it's probably going to look somewhat close to that. Alright, there you go. Now, that takes care of the big problem, but today we're going to go over something that is going to be very, very useful. It's not particularly applicable to this section, although since this section is all about this chapter is all about the uses of derivatives, I suppose it fits. But L'Hopital's rule is really a way to figure out limits. If you remember in the past, we looked at some limits that were very difficult to figure out. We looked at a lot of limits where we'd get a function. If we plugged in 0, it would be 0 over 0. And, that wasn't so good. We couldn't do anything with that. We needed to use algebraic manipulations. Well, L'Hopital's rule offers us a way to not have to do any of those algebraic manipulations. Now, I'm just going to write out the rule, basically. I'm not going to write out the textbook definition. I'm going to show you what the rule is. Basically speaking, if you have L'Hopital, it's like l'apostrophe hospital's rule. Some people omit the S. Technically, it wasn't even invented by L'Hopital. It was a Bernoulli invention who created a lot of these. But L'Hopital spent a lot of money, so he gets his name. And that means that every person who teaches math gets to explain that it's not really his rule. Anyway, more about L'Hopital's rule. Basically, if you have if you have a function that has an indeterminate form, that could be 0 over 0. That's a very good indeterminate form. There's also infinity over infinity. That's an indeterminate form. But there's other types. Other indeterminate forms. You have infinity minus infinity. Can't have that. What's infinity minus infinity? We know that infinity plus infinity is just infinity. But infinity minus infinity, no real way of telling what that is. There's also 0 times infinity. Can't really have that. And here come some exponential ones. These are a little bit interesting. You have 0 to the 0th power. That's indeterminate. You have infinity to the 0th power. And then you have probably the most interesting one. And that is 1 to the infinity power. Now, 0 over 0 makes sense. Infinity over infinity makes sense. Infinity minus infinity makes sense as to how you wouldn't know what that is. 0 times infinity makes sense. 0 to the 0th, okay. Infinity to the 0th, alright. But what about 1 to the infinity? Shouldn't that just be 1? 1 times 1 times 1 times 1 times 1 times 1 is always going to be 1, right? Well, it turns out that the reason that 1 to the infinity is an indeterminate form, as you may know, which you may know, is that when we were talking about calculus, if you remember from very early on, I said this really isn't a course in what something is. It's a course that looks at limits, where things are almost. It's not really a discrete quantity. We're not really looking at 1 in calculus. We're looking at something that's almost 1. It's almost 1. Not quite 1. But there's a huge difference whether it's 0.999 to the infinity or 1.001 repeating to the infinity. It's going to be a difference. So, that is why those are indeterminate forms. Now, if you have an indeterminate form, you can do some fun tricks using L'Hopital's rule. And L'Hopital's rule basically says, here's the gist. For a 0 over 0, or an infinity over infinity, this is how we're going to use L'Hopital's rule. If we need to figure out the limit of some function as x approaches a, just some number a, of f of x, g of x, and we end up evaluating that and we see a 0 over 0 or infinity over infinity, well, there's finally a shortcut. This is the same as saying the limit as x approaches a of f prime over g prime. F prime x over g prime x. Please note, this has nothing to do with the derivative of the function. This is just a fun trick that happens to work. Let's see it in action. I'm going to consult the book for a good example here. There's a lot of good examples, actually. Okay. Yeah. This looks pretty good. Let's find the limit as x approaches 1 of the natural log of x over x minus 1. Now we know. Let's just try that direct substitution again. The natural log of 1, okay, well, we're going to get zilch. And 1 minus 1, once again, 0. So we have 0 over 0 with direct substitution. Please note, it needs to be 0 over 0. If it's 3 over 0, 0 over 0. We have 0 over 0. We've got direct substitution. We can use L'Hopital's rule. Let's do it. That means that we're going to take the derivative of the top. This isn't the quotient rule. We're not finding a derivative. We're going to take the derivative of the top, ln x, 1 over x, over the derivative of the bottom. X minus 1, the derivative is simply 1. So we're saying that limit, the limit as x approaches 1 of ln x over x minus 1, is the same as the limit as x approaches 1 of 1 over x over 1. And if we go ahead and use direct substitution now, we get 1 over 1 over 1, which is 1. So the limit of this function, ln x over x minus 1, turns out to be 1. And that's how we use L'Hopital's rule. It's going to make calculating limits a lot easier. A lot easier. Now, some other interesting things that you can have happen is you can have indeterminate products. Like I said, 0 times infinity. If we've got the limit as x approaches 0 from the right of x ln x, well, what we can do here, we have let's go ahead and plug in 0. We have 0, direct substitution, times infinity. So, that's that's not really a good thing. That's not really a good thing. I mean, it's going to be negative infinity, but there's nothing we can do with that, because how do we figure out what f prime is and g prime? It's very simple. We just go ahead and arbitrarily make a quotient out of this. So, x ln x is really the same. X ln x is the same as the limit as x approaches 0 of ln x over 1 over x. We just created a quotient out of that by dividing by x. So, now we can try direct substitution, and we're going to get negative infinity over infinity. We're going to be able to use L'Hopital's rule now, and let's go ahead and do it. Write LH, or you can write an equal sign with h above it. 1 over x over negative 1 over x squared. And we can go ahead and we can call that the limit as x approaches 0 from the right of negative x. Just cancel these, and we can plug in 0. Negative 0 equals 0. So that's the limit for that product. So you can see, whenever you have an indeterminate product, go ahead, take one of the terms, make it a reciprocal, and turn it into a quotient. Now, we also have indeterminate differences, infinity minus infinity. A good example here, this is ugly, but it's worth mentioning. The limit as x approaches pi over 2 from the negative side is secant x minus tangent x. If you remember your trig functions, you'll realize that this is in fact infinity minus infinity. We can't have that, so we're going to use a common denominator. Limit as x approaches pi over 2, remember, from the left. We always want to use sine and cosine when possible. Secant is just 1 over cosine. So we have now 1 over cosine x minus sine x over cosine x. That's what tangent is. And we can use that to say that this is the limit as x approaches pi over 2 from the left, 1 minus sine x over cosine x. It's the exact same. They're the same thing. So now we can use direct substitution. And with direct substitution, we find that this limit is the same as negative cosine x over negative sine x at pi over 2 from the left, and that's going to be 0. So like you can see here, indeterminate differences, you're frequently going to be seeing them with trig functions, because it's very easy to make a common denominator, although you can do that with any function. Well, you can do that with several indeterminate differences. The final thing we're going to talk about with L'Hopital's rule is what to do when you have exponential functions. If you have an exponential function, well, I'm just going to show you this. This is the best thing I can show you. The limit as x approaches 0 from the right of x to the x power. That's really hard to do, because that's 0 to the 0. We don't know what that is. But it's actually pretty easy. What we're going to do is we're going to exponentiate the function and use the natural log. Let me show you how this is done. This is the same, x to the x is the same. Remember, e, the inverse of the exponential, is the natural logarithm. So, e to the ln x equals ex ln x. That's just one of the properties of logs. Now, we can use L'Hopital's rule, or we're going to show how we can use L'Hopital's rule to make x ln x equals 0, and therefore we have the limit of x to the x equals 0 to the 0. Therefore, the limit as x approaches 0 from the right of e x ln x is the same, which is also the same as limit as x approaches 0 from the right, of e to the 0th, which we know is 1. So the limit of this function of x to the x near 0 is 1. Finally, to show you how we went through all of that madness, it's important to look at exponentiating these tricky things. So let's look at the limit as x approaches 0 from the right of, whoa, man, they really have some good ones here. 1 plus sine 4x to the cotangent of x. Remember, cotangent is going to be cosine over sine. So, what we're going to do, if we let this right here, let's let this quantity equal y, just for the time being. Just for the time being. Okay, so if that equals y, then the natural log of y is going to be cotangent x, right? Laws of logarithms here. Can take down the exponent times the natural log of 1 plus sine 4x. Okay, now you might be seeing something here. We could plug 0 in right here. We can take the limit as x approaches 0, and we'll see that here we're going to get, well, we're going to get something indeterminate, but we're not quite there yet. Let's go ahead and let's realize that we can rephrase it, we can rewrite this. By having cotangent, we can take the reciprocal and be working with tangent, which is frankly a lot easier to work with. So the limit as x approaches 0 from the right of the natural log of y is the same as the natural log of 1 plus sine 4x over tangent x. Tangent, better to work with than cotangent. Now, with some very creative manipulation, you can go ahead and you can find out. I'm just showing you. If I've lost you, I apologize. This is kind of tricky. You're not going to be using these most of the time. It's mostly just going to be f prime over g prime, and you're going to be done. But you need to look at this. Basically, you can take all of that, and you can find the limit as x approaches 0 for cosine 4x over 1 plus sine 4x over secant squared x. That's the derivative top and bottom of the previous, which was, in case you forgot, the natural log of 1 plus sine 4x over tan x. Derivative of tan x, secant squared x. Derivative here, you've got the ln, so it's the chain rule. Okay, now we can plug 0 into this, and we'll get 4. But we're not done. Because remember, the ln y now equals 4. So, what we need to do to get back to the original is exponentiate. So e to the ln y equals e to the 4th. E is the inverse of the natural log, so y equals e to the 4th. That's your real limit. In other words, whenever you've got an exponentiation, whenever you've got an indeterminate exponent, you're probably going to need to use that trick where you take the natural log of the quantity and figure it out there. Just remember that your final answer is probably going to be either 1, 0. Now it's probably either going to be 1 or e to the something. It's going to be e to the something. Because you have to exponentiate at the end. Well, that turned out to be much longer than I planned. The next 2 classes, or the next 2 lectures, will be fairly long as well. So just prepare for those, and I'll see you next time. Thank you very much for coming by. Bye-bye now.